All right, good afternoon, everyone. So this is the Booting Your OS Across NVMe-oF Fabrics talk. My name is Charles Rose. I work for Dell, and I have Curtis Ballard here. He works for HP, and we've been working on this for at least a couple of years, and Curtis probably longer than I have. So at Dell, I primarily work in the Linux engineering team, working with Linux distribution vendors, enabling new technologies in Linux for Dell Technologies. So with this talk, I will let Curtis introduce himself first and go through some of the specification aspects, and I will take over on the reference implementation that we've been working on as part of the work group, the boot work group, and then go into the proof of concept work that's available publicly today. So I'll hand it over to Curtis.
Thanks, Charles. As Charles says, I'm Curtis Ballard. I work for Hewlett-Packard Enterprise in the storage organization. Represent Hewlett-Packard Enterprise at NVM Express and was part of the small group of companies that put together the Timberland SIG that hosted the software development to enable the reference implementations that we're going to be talking about today. So here's a quick intro to our agenda. We've got a little bit of an introduction to the boot specification. Then we're going to talk about why we're standardizing booting from NVMe and NVMe-oF namespaces. A little bit about some of the ecosystem cooperation, how you configure things, the reference implementations, and hopefully plenty of time for Q&A. If you have any questions as we're going along, though, please don't hesitate to interrupt and ask. I won't spend a lot of time on this slide. You guys probably have seen variations of this many times and are tired of it by now. But NVM Express Incorporated is the parent organization of the NVMe interfaces. The promoter group on the right-hand slide of there lists a number of companies that, if you were in any talks this morning, this has been shown a couple of times. And so we got a little over 110 member companies involved in NVM Express today, working on optimizing high bandwidth, low latency storage. And it has a variety of specifications. We'll talk about those a little bit more in just a few slides. So you may have seen this slide as well, or variations on this slide. Here's a picture of the NVMe family of specifications. We're on version 2.0 of the specifications. We released a variety of 1.x specifications, and then as the industry grew and we got more and more capability into the specifications, we found that it was getting quite lengthy, and we refactored it, which set up the structure that really made this NVMe over Fabric boot work a lot easier. So broke into a family of specifications with the NVMe base specifications that's shared by all of the different specifications that are product specific. Then there's a set of command set specifications for things like key value drives and your standard NVMe block drives. Transport specifications for the different PCIe, RDMA, TCP, and then specifications that work across the stack. The management interface specification is the first one that's been with NVM Express since the early days, and not part of the 2.0 family of specifications at release, but now released in November of 2022 was the NVMe boot specification. So that's been out about a year now, and we've been frantically working to turn it from a fledgling specification to reality. And the group that's been doing that is the NVMe boot task group. There's actually two different groups that have been working on this. The NVMe boot task group has been creating the specification, and there's another group that is called the Timberland SIG. That is a smaller group of companies that have been actively developing a reference implementation alongside this boot spec. If you've seen other versions of this talk as we've come along through the process, this boot task group has just grown and grown. Currently has 41 companies in it, and it's one of the little purple boxes there in the NVMe task groups. Not especially interesting in and of itself in that respect, but the refactoring to 2.0 really set up the structure that enabled this group to work a little bit separate from the rest of the NVMe specification. It's a little bit of a different skill set, a little bit different people and companies that are interested in booting across the fabric versus the people that are working on the command set specification for your standard SSDs or storage arrays. For this group, the co-chairs are Doug Farley with Dell, Phil Caton with Intel, and Rob Davis of NVIDIA. None of those are here with us today, but we've got Dell represented and Hewlett-Packard Enterprise. So hopefully this is kind of self-evident, but why does NVMe technology need a boot specification? If you've been working in storage networking for a while, all of the technologies that have been very successful have had a way that you can boot a server directly off of the BIOS in the server across the fabric to the storage device. For fiber channel storage devices, being able to boot over fiber channel has been built into the operating systems and fiber channel HBAs for a lot of years. It's used extensively in computing this diskless. So you can have servers that boot entirely everything over the network. iSCSI, the industry learned that this was a necessary functionality for iSCSI, and it was kind of developed ad hoc after the fact, and we learned a lot. And so we've been trying to take the learnings from iSCSI and apply them to NVM Express and do it better the second time around. So I mentioned iSCSI. We leveraged that. We didn't do everything exactly the same, but we leveraged it and used the pieces that were solid and that had been developed well. It already had defined a mechanism of enabling the boot from the OS and a handover mechanism that was called an iSCSI boot firmware table. Actually still is called an iSCSI boot firmware table. That contains all of the pre-OS information that has to get passed up to the OS. So the obvious model was to continue with that and extend that boot information table into NVMe over Fabrics. So when it gets to NVMe and NVMe over Fabrics namespaces, we leverage those iSCSI lessons, as I've said, and we copied the concept of that iSCSI boot firmware table, and we're creating a NVMe boot firmware table so that things are very similar to the way those two different systems work. So for boot from NVMe, we created this thing called the NBFT that's pointed to by the arrow over there on the right. That's an entirely new NVMe boot firmware table that copies over the constructs that we need for booting from NVMe. A little bit about the standardizing the process. As we said in earlier slides, the boot specification was published on nvme.org in November of 2022. That defined the constructs and the guidelines for booting from NVM Express over the various SPARC transports for Ethernet. This version 1.0 specifically only defines booting over NVMe TCP. If you're familiar with NVMe PCIe, we've been booting off of NVMe PCIe for quite a long time. And so that is native OS functionality calling into the PCIe layer. When you attach an Ethernet drive, that native boot from PCIe isn't able to see the Ethernet drive. So there's a lot of work has to be done to discover and connect that Ethernet drive before you can hand it over to the OS boot. So this version specifically defined for NVMe TCP to leverage the TCP work that had already been done for iSCSI. It defines the boot stage and flow in a UEFI pre-OS environment, and then the implementation guidelines and best practices for getting up into the OS. It took a lot of ecosystem work to do this. At this point in the game, almost everything is completed. We have reference implementations out there. Products are starting to show up in the marketplace that do this, and it Doesn't look too complex, but it took a lot of work to get there. We had to work across 3 different industry standards bodies and then a open source development organization as well. So the first ones you might be familiar with is UEFI Forum. They've got the ACPI specifications and the UEFI system specifications. We had to work with the UEFI Forum. The NVM Express Boot Task Group defined proposed tables to go into the UEFI specifications following the UEFI models, and then member companies worked with the UEFI organization to get those introduced into UEFI. We created the ACPI XSDT signature table that defines the NVMe over Fabric's device path extension support for NVMe boot from UEFI. That enables connecting those two together. We don't have to go through all of that today, but if you want to talk to us out in the hall, we'd be happy to go through line by line with you. Then we had to work with the DMTF organization. The DMTF organization, we worked with them to get a standardization of the Redfish NVMe-oF secrets registry so that you can do authenticated boot, that Charles will talk about a little bit further in his talk. And so here's the DMTF Redfish model for storing NVMe-oF secrets in the Redfish object model. I had to define some key types. I had to define secure hash allow lists and some tables there on security protocol types. And then, of course, we've already kind of talked about the NVMe over Fabric's boot spec 1.0 that defines how you can boot a NVMe over Fabric's device. And with that, I will hand it over to Charles, who will talk about how these pieces work.
One question about the security. Does it need anything in addition to what is defined for security through the TLS addition to the NVMe over TCP?
Okay, question on security. Does the NVMe over Fabric's boot need anything beyond the TLS specifications that are so the NVMe over Fabric's boot model is designed to take advantage of and use the NVMe over Fabric's authentication with the DHH MAC chap and the TLS secrets that are defined in the NVM Express base specification that the FMDS group maintains. So it's all built to use all the same Fabric's authentication. The pieces that had to be done new for the boot are a loading and storing of the secrets for the authentication mechanisms to work.
Thank you, Curtis. I should apologize for my voice. As soon as I got off the plane, there's something that attacked me, I guess. So it seems like allergies. But so like Curtis was saying, the NBFT table is the primary deliverable from the pre-OS environment. So in this case, we used UEFI Tianoco EDK2 to create a reference architecture that the community can then use and model it for various different other platforms. So NBFT is the mechanism to hand off the config data from the pre-OS driver that's created by UEFI to the OS. And so the pre-OS administrator configures the subsystem NQN, IP address, namespaces, security information, etc. And all of that is put into the NBFT as part of the pre-OS configuration. And into this information, we can also add optional fields. For instance, the specification also allows multiple NBFTs to be defined by option ROMs, for instance. An aggregation of all of that will then get presented to the OS. And then OS can continue the boot process from there on. So as you can see in the figure on the right, the NBFT consists of 3 major elements. So you have the header, you have the control descriptor, and then the host descriptor. And optionally, we have the extended details that can be presented to the OS through population of several lists from descriptor elements and properties, example, relevant host, subsystem, controller information, etc. So this is the information pre-OS driver needed or needs to complete the network boot. And at this point, the system is ready to transition to the OS runtime. And one of the advantages of this over the iSCSI boot of the IBFT is to be the ability to share namespaces other than the boot namespace. So this can include non-boot namespaces or data stores that you just want the system to be able to access. So this helps use cases where you want to have volumes in addition to the ESP that need to be available to the host OS. So as discussed, the public reference implementation is based on UEFI EDK2. The reference code was developed by a subset of the NVMe boot task group members, so Intel, Dell Technologies, NVIDIA, SUSE, Red Hat, HPE, and VMware. And the reference code can be retrieved at that address. If you cannot see, it's github.com/Timberland-SIG. And all of the stuff is available, everything that we're going to talk today. And the code is released, or most of it is released. The stuff that is not released will be released under BSD 3 clause or appropriate open source licenses. So let's get into some details about the UEFI boot sequence and what happens during booting over NVMe in a UEFI environment. So this is the obligatory slide that we are required to show as part of the Tianoco EDK2 build specification. And as a primer, the UEFI spec defines several phases. None of this is unique to the work that we're doing, but this is regular UEFI boot process. And the EDK2 implementation is what our proof of concept that we will discuss is based on. And the NVMe boot spec and the reference implementation affected several of these steps, as we will go into in the next several slides. So there are these 7 of these we'll quickly go through. Probably relevant pieces are just from 2 to 6. So the first primary phase after platform security completes is a pre-EFI or a PEI phase. And in PEI, initial configuration context is gathered. And during this phase, boot attempt configuration that is stored in UEFI variables is collected. So, and this configuration consists of administrative configuration relevant to pre-OS driver. In the next phase, such as subsystem information, NQN, IP, security parameters. And it's important for the later reestablishment of the configuration context by the OS that there's consistency between these. So in our reference implementation, some of this is currently saved with an EFI shell tool, which parses the config file and writes UEFI vars, and I'll show you some screenshots on how that looks. We also recently have a HII that was developed, and it's available again on the Timberland SIG. So you can go there, download the code for this, build the OVMF, fire this up, and test it if you like. In the future, there may be BMC-based approaches to interface with the EFI HII variables and simply simplify filling out those in a more programmatic manner for large-scale data center fleet-style workloads. So that's the first part. So the PEI basically tries to collect information that is already present in the system through either the HII, a command line tool, or future BMC style interfaces. And then the next phase, PEI, is followed by the Dixie phase, driver execution environment, as the UEFI folks call it. So in this Dixie, drivers of various devices and interfaces are loaded as protocols, and ultimately things such as NVMe-oF, Fabric Transport are given a block interface. And this is where the primary new work of our reference implementation happened. This driver ultimately needs to read the administrative context from the previous step, and set up new network connectivity to allow for the connection to relevant NVM subsystems. This is also where we finally gather the namespace specific information for population into the NBFT later on. And at the end of this Dixie phase, the driver load is where the configuration for the NBFT ultimately stored away to be accessed by the OS part of the ACPI NBFT. So just to recap, the PEI phase is where we collect configuration as variables. The Dixie phase is where the network is configured and the connection is established. And once successful connection is established, all of that information is populated into the NBFT. So in this, so I have an example. There are optional discovery and authentication steps. The reference implementation doesn't implement the authentication yet. I think there was a question already on that. But the variables are present, and it's in the boot specification for easy integration. So the reference implementation supports a DDC, or a direct discovery controller, and switching to other controllers to connect to the subsystem, but it doesn't yet support the auto discovery, that is the CDC method of discovery. Step 4, Dixie is followed by the boot device selection phase, BDS. And this is where the boot manager entries are matched to EFI partitions via UUIDs. And the system policy controls which of these namespaces may be chosen as boot device and which order they're offered for booting by their EFI device path. In some implementations, such as EDK2, a boot manager or other selection screen is typically found. So as you can see on the picture, they usually help to correlate the specifics of the device to your entry. So in this picture, you see the boot managers found our NVMe-oF fabric messaging protocol with the Linux distribution installed on its block device. That's on the right-hand side. Apologize if it's too small. The slides should be available after the talk. So once the boot device is selected and the user, for instance, or based on a system timeout, it goes to the next phase, which is the transient system load phase. And this is where the OS image is loaded and UEFI to OS execution is handover is performed, or at least started. It's transient because UEFI may hand over execution to other applications or drivers during this phase. However, access to the native connections that the UEFI drivers created is still possible. So think of something like Grub, which will load at this phase, and it would continue to use the connections that were established by the Dixie and treat it as if it was a regular block device with an ESP partition optionally on that, or it's just a raw device. It's also possible for drivers and applications to still create new ACPI tables during this phase. Like I mentioned, you can have more than one NBFT table itself. But a lot of our testing initially has occurred with just a single NBFT. By the end of this phase, however, the NBFT has been generated, stored in memory for the runtime OS to access. Then the final phase that's relevant to our discussion is the runtime phase. And now that the OS has loaded, and this point for Linux users, this would be when the kernel has been loaded. So you had grub, at which point you still had the block devices that were created by the Dixie, but at this point, the Linux kernel has loaded, and the OS may choose to use the NBFT data or its own existing configuration to reestablish connectivity to devices configured during the pre-OS environment. So typically in runtime, OS is now completely disconnected from the pre-OS drivers such as UEFI, and at this point, OS will choose to read the NBFT in order to set up the appropriate networking interfaces, device selection, routing, binding, etc., and configure any authentication or discovery relative to that network, and ultimately reconnect to the NVMe subsystem in question. So on Linux, this would be an NVMe discover and an NVMe connect, for instance. So at which point you have a new connection established to the same subsystems. So in runtime, there can be some differences between consumption patterns of a typical OS versus installation environment for the handover or initialization. For instance, if for For the OS runtime, if the OS chooses to use the NBFT, it may use the NBFT provided information as is, its own configuration, or utilize both a local administrative configuration and a subset of content from the NBFT. And this is completely OS vendor specific, and the distributions can decide whatever they want to at this point. However, for an OS install, this can be a little different. And even without a bootable namespace present, that's a ESP, UEFI system partition, an OS installer may still need data from the NBFT to be populated so that it can establish connection to a new boot device in addition to locally administered devices. And as previously alluded to, this is an important case where the NBFT will likely contain unconfigured namespaces that the UEFI BIOS may have marked as otherwise unavailable or unbootable. So this is still crucial for a successful installing and loading of OS onto the NVMe-oF fabric media. So this ultimately then allows for a single configuration management ecosystem to program the relevant configuration that may then propagate to pre-OS and OS drivers, paving the way for future fleet management. So I guess the source of truth really depends on the environment, where if you have a one-point management plane, none of this exists, but if you have a one-point management plane, is that plane going to communicate with a BMC-style device and push in all of your configuration at scale, and then the OS installer would pull all of that information via the NBFT and do the deployment, or is this going to be orchestrated through an OS deployment style framework? I think that really is implementation specific. So now on to our reference implementation. So we saw how the actual boot of a UEFI system typically functions and where NBFT fills in. So the reference implementation that's available on GitHub, TCP, Timble, and SIG is needed to aid developers, folks in this room, across the industry to enable a consistent boot over NVMe capability. So the implementation consists of both pre-OS and OS runtime software. And as you can see, for the pre-OS, a new UEFI driver for the TCP Transport for EDK2 was developed. And in the OS boot and runtime, Linux implementation that exposes the NBFT and consumes the NBFT was developed that enables use of common OS tools. We'd like to start with a discussion of the evolution of the proof of concept architecture towards a reference implementation, and then go into the tools that were developed to support booting NVMe-oF fabric along the way. So two big pieces, the pre-OS. So for the pre-OS, so this diagram attempts to show, I'm not sure how visible it is, how the design evolved from initial concept to a reference implementation. So the diagram on your left was where the concept started off, but what we landed up is what's on your right. So on the left, we show the original proposal in green are the elements we believed that could be leveraged from existing ecosystems, components, when we had initial discussions with the ecosystems and community. And in blue are the items we planned new development as of UEFI and NVMe-oF fabric behavior. In particular, we expected to leverage the implementation of NVMe-oF fabrics in SPDK within the EDK2 driver. So initial concept was focused on just creating the basics for the driver itself and attempting to reuse those community assets like SPDK, so we didn't have to go reinvent a whole new stack. But then, in reality, on the right is the implemented architecture for the current reference implementation. And you can see how we modified or added to the existing components. So as the reference implementation evolved, we were able to develop an NVMe-oF fabric library. So that's around the middle of the screen as a POSIX shim that made it possible to directly reuse SPDK transport layer. So we didn't have to create yet another bespoke ecosystem implementation. That would have required associated interoperability and maintenance and all those other problems. So this ultimately led us to build an extensible EDK2 driver to drive the framework around those interfaces shown in brown, and allows us to reuse much of the existing UEFI interfaces in gray on the right-hand side that are present today. So in addition to the driver, we found that we needed an environment we needed a command line to manage the environment. How do we input details on where's my subsystem stored, what's the IP address, what's the VLAN details, and all of that stuff. And for that, we created a configuration tool that made it easier to automate and interact with the UEFI pre-OS driver. This is initially used for testing, but there's nothing stopping anyone from using this to automate stuff. So this command line tool was inspired by Linux's NVMe CLI, and it was designed to facilitate the same basic diagnostic configuration that Linux has from its user space, and has allowed us to test our interoperability of the pre-OS reference driver with the OS. So in some example cases, so here we have the NVMe-oF fabric command providing a list of known NVMe-oF devices that have been attached and their associated attributes, if you see on the left-hand side. So things like the CNS03, namespace, UUID, capacity of the namespace, model, etc. So additionally, similar to the Linux command on the right-hand side, we have an example of how the NVMe CLI application, UEFI application, can also be used to connect to NVMe-oF fabric devices. And it too has similar argument structure as the NVMe CLI, so you have a -T, -A, etc. And so when a user types in all of this and hits enter, and that's going to establish the connection, do a discovery if it's required, and then eventually go, if the connection is successful, go populate the NBFT at the end of that whole process. So up until July, that's all we had, and that's the only way we would be able to test this stuff. July, we added support for a HII environment as part of the EDK2 toolset. So now it's possible, if you see on the top left-hand side, to go and go into the F2 screen or whatever the EDK splash screen is, and go to the device manager. And similar to iSCSI configuration, now we have a NVMe-oF fabric configuration. And when we select that, you get the screen on the right, and you can go and populate the host NQN, host ID, etc. And then you have 4 attempts that it shows up that can be configured. And so each of these attempts, for instance, on the bottom left, you'll see you can enable the attempt, and you can pick which device or MAC ID the attempt will use. And is it going to be IPv4, IPv6? Is it going to be DHCP or static? And then you can put in information about the subsystem, TCP IP addresses, etc., security information, etc. So once you put in all of that, save this, and on the next reboot, it would do the same thing that NVMe CLI did in the previous slide, and would, at the end of it, would populate the NBFT again. So leaving the pre-OS environment, let's talk about the transition to the final OS runtime. So for the runtime in the Linux implementation, there are 3 areas of basic focus here. You have the platform, the kernel, and then the user space in the Linux context. So majority of the new work, if you see in the green, is in the user space. So in the middle, if you see today, the Linux kernel exposes the NBFT from ACPI via sysfs to user space. So if you, I think kernel 6.0 got support for that. It's a 1-line patch which says if you find an NBFT in the XSDT, just create a sysfs file node for that. And this can be NBFT. If you have just one NBFT, it'll be an NBFT. If you have more than one, it'll be NBFT 1, 2, 3, and so on. User space tools allow for exporting and consuming NBFT content. And what we did with the user space tools is basically for the reference implementation, the primary consumers are Dracut and OS installers. So if there are Linux folks in the room, you'll know what they are. And we we classify them as systems management tools, and they can get standard representations from the NVMe CLI or libNVMe libraries and use them to generate the NVMe-oF fabric config and reconnect as normal. So NBFT shows up in the platform. The kernel detects that's an NBFT, creates a file node, and in the user space you have libNVMe and NVMe CLI, which have support to parse the NBFT table. And because it's bulk of the code is in libNVMe, libNVMe also has Python bindings. So now you have tools like Network Manager or Wicked or NetPlan, whatever else. They can directly interface to that and parse the NBFT, configure the networking, and then use NVMe CLI to do the connectivity over that. So, and all of this development has been done using the standard KVM QEMU workflow with the EDK2 OVMF output from the pre-OS code available. So an individual developer with just one laptop can now simulate an NVMe TCP subsystem. So you can have a virtual machine running NVMe-T that acts like your target. And then you have a second virtual machine running the EDK2 OVMF from Timberland, and that can be your boot target. And as of now, it should also have the HII built into it. So as we previously mentioned, in our reference implementation, we had to modify tools like NVMe CLI to support the NBFT. And all of this code is merged upstream with NVMe CLI and libNVMe. So, and this should already be in some of the distributions by now. So here's an example of an output of NVMe. There's a new command called NBFT show that got added. And so this example shows two namespaces, for instance, that NVMe was able to go and parse out from the NBFT for two namespaces present on multiple controllers of a single NVMe-oF fabric subsystem that was found via its discovery controller. So there are two HFIs. You see the two MAC addresses right in the middle of the screen, and then you have those multiple paths to two different controllers that NVMe was able to extract from NBFT. Now, this does not guarantee that the connectivity to these were established. That is done using the NVMe connect NBFT command, and that would automatically go and parse and do the connect, which is done by OS installers and even early boot scripts like Dracut. So NVMe CLI supports a human-readable format like this, columnized. It's very easy to read, but it also supports a machine-readable format that outputs a JSON format output. So this can be easily parsed using JQ. All of this is also available through Python bindings if you can interface with libNVMe. So as you can see in this example, so NBFT starts off with the required host descriptor. I guess you cannot see, but trust me, it's there. So it has the host descriptor on the top, and then followed by the subsystems. So you have the subsystem definitions, and then you have the HFI definitions for each of your interfaces. So every MAC ID will have one section under the HFI. And then it has a discovery section as well for discovery controllers. Right now, this is more of a dummy. NVMe CLI, at least on Linux, does not know how to process this. It would directly go into the subsystem, pick each of the records, and start connecting to them. So as we said, the reference implementation is the collaboration of a lot of different work coming together, and our proof of concept for the NVMe-oF fabric is based on OpenSUSE and Fedora. So right now, we have elaborate proof of concept documents that have been written down and published on the Timberland SIG GitHub page. You would find one for OpenSUSE and one for Fedora. And what are the things you would need for this? So you would need an Intel-based host running a current version of OpenSUSE or Fedora, and because you need a connection to the internet and have privileges to be able to run QEMU or KVM, and you need virtual networking and some NVMe-oF fabric subsystems. This could be another QEMU running NVMe target software. And that should be enough for a typical developer to get started with this environment. So as I speak, OpenSUSE 15.5, OpenSUSE Leap, has all of the OS pieces that are required. So if you boot up OpenSUSE Leap ISO on an OVMF that is from Timberland SIG, it should be able to detect the NBFT, and if there are NBFT entries, automatically connect to them and present them as install targets, and you should be able to install the OS and reboot the machine and boot into that system. And Fedora should be similar. I'm not sure if it's been merged into any Fedora distribution yet. So the reference implementation proves out the functionality of the NVMe boot spec by enabling booting of NVMe devices over NVMe TCP. It does not implement all the features of the spec. The spec is also continuing to evolve with new features and capabilities. And so some of the enhancements that the reference that the reference architecture does not cover, and we would require, or we would invite community to participate, is support for authentication and TLS, support for DMTF redfish secrets, as Curtis alluded to earlier, and additional OS installer support. So if you're an OS vendor in this room, we definitely hope you can collaborate with this group. And the NVMe boot spec standardizes the basic constructs to boot over NVMe TCP. However, more can be done. And these are some of the open items. Investigate booting over additional transports. I think CXL seems to be coming up in a lot of our conversations. But and then big namespace quantities, multipath topologies, device tree for embedded DPU-style deployments, and setting NVMe over fabric boot entries in the OS using command line tools like EFI Boot Manager. So talking about transports, we'll wrap up with this slide. Just to highlight the ease with which supporting additional transports are. So as we previously discussed, NBFT contains a transport-specific descriptor from which we outlined this template in the NVMe Express Boot Spec. To support additional transport, it's necessary only to add transport-specific pieces to the NBFT's HFI transport info descriptor. There's a minor mandatory header as part of the HFI transport info descriptors today, and then other transport descriptors, specific flags and configurations as is needed. For example, from TCP today, those HFI constructs are things such as MAC address, VLAN, IP addresses, and gateways. And these are minimal things that are required in order to establish connectivity from host to a subsystem. Keep in mind that if a transport doesn't already have an existing implementation in something the boot spec and UEFI provides, then extensions may be required there too. And
I just want to make sure I heard you right. So if I want to boot over SD, I have to update the boot specification as well as the software. Is that correct?
That's correct. Curtis?
Well, the question was, if I want to boot over Fibre Channel, I have to update the specification as well as the software. And Fibre Channel has its own boot over Fibre Channel mechanisms already existing that aren't device type specific. So the boot over Fibre Channel uses existing boot over Fibre Channel mechanisms, and that works without the work we're talking about here today.
All right. So with that, we thank you for your time, and we invite everyone to come and join in the community, help us continue to evolve this ecosystem. And as always, if you would like to see any of the specifications that we've discussed here today, or the reference implementation, the OVMF payloads, artifacts, and the links are here. And thank you so much, and I think we have some time for questions.
I just wanted to ask, and good presentation, thank you, Johnson, for this. I know you talked about requiring support from other operating systems. Any comments on when VMware is getting to this?
I do not know. Curtis.
Yeah, we're not allowed to comment on partners that aren't present today, so can't say anything about their plans, sorry. The question was, any comments on VMware's intent is to support this, and we're not allowed to comment.
It's not already there.
I don't know that I'm even allowed to comment to say that. I'm sorry. Yes?
So is multipath supported? Is it planned to support multipath?
A lot of the pieces to support multipath are done, but multipath support isn't fully developed and tested yet. But it has been designed to be able to support the multipath. Do you know the multipath implementation better?
You're
okay.
Right. Yeah.
Yeah. So there's still some pieces to be done there for a full multipath.
Yeah, the only OS we know for sure it works is OpenSUSE Leap. Yeah.
Yeah, and Fedora.
I know.
Yep.
Well, the difference is Fedora requires you to pull in more upstream pieces, but Leap 15.5 has everything baked. So all you need is the ISO.
Any other questions?
So is NBFT only unidirectional, meaning UEFI provides it and the operating system layers consume, or is it the other way around also, is something which you have considered?
So the question is NBFT unidirectional from the pre-OS environment to the operating system? And the answer is yes. It's meant to be a manifest that is created by the pre-OS environment and handed over to the operating system. Now, we've had discussions on, is it possible to configure or change NBFT components from within the OS? I guess those are things we can have a discussion about for specific use cases. I'll let Curtis comment more on that as well.
I don't know much more than Charles. There's been talk about when you're in the operating system, potentially we could provide some tools that you can load NBFT information that would persist and be consumable on the next reboot. But that's still TBD and work in progress if there's a use case for that.
But if you have an idea, welcome to join the work group and propose it.
I'll probably think of the
Yeah, yeah.
Nothing else? Okay.